Hello everyone, and welcome to this video on the orthogonal projection of one vector onto another vector. Right, so in this video, I'm going to define, what the title means. What is the orthogonal projection of one vector onto another vector, and I'm going to go through and show you what that means, in particularly in the vector space R2. Right, two-dimensional Euclidean space under the dot product, and we'll develop a little formula for the projection of one vector onto another in R2 under the dot product, and then this will be generalized to just any inner product space. But I wanted to go through first R2 so we can visualize some things and motivate the formula. See where it comes from. Okay. So the orthogonal projection of one vector onto another vector. Right. So again, like I said, I'm going to start off. Let's suppose we're in R2, right, two-dimensional vector Euclidean space, under the standard inner product, right, where the inner product of two vectors is just the dot product, right, the standard inner product, the Euclidean inner product, the dot product. All right, so if I have two vectors in R2, and suppose I drew those vectors both starting from the same initial point, maybe from the origin or something. So I got vector u here and vector v here. Right, so u and v. The orthogonal projection of u onto v is just the vector on the line containing v, or the span of v. Remember, if I were to extend it, I could draw a line containing v if I wished. But it's the vector on the line containing v that is closest to vector u. It's the shortest distance, right? So in a way to form this, a way to see this in R2 especially, to project u onto v, imagine or draw an orthogonal segment from the end tip of u to the line containing v, which I've done here with this dotted black segment. So from the end tip of u, I drew a little segment that's orthogonal to the line containing v, or in this case vector v itself. Right, and this is the shortest distance from the tip of u to the line with v. Right, if you traveled any other distance, it would be a longer distance. Right, so the orthogonal projection gives us the vector whose end is the shortest distance from the end of vector u. Now, because I'm dealing with the dot product on Euclidean space, orthogonal has the same meaning as perpendicular. So here my orthogonal segment, does form a 90-degree angle, is perpendicular to the vector, the line containing vector v here. Then this vector, right, from where the vectors u and v meet, to this point that's directly beneath vector u, the end of vector u, this vector is called the orthogonal projection of u onto v. Right. And the way it's denoted in most texts that I've seen is, projection of vector u onto vector v. So proj, then in parentheses the vector that's being projected, vector u, and then a subscript under the proj, under the proj, is the vector that's being projected onto. So this is the orthogonal projection of vector u onto vector v. Alright, so I've got this same picture drawn up on the next page, just a little bigger. So here it is again, right? Similar picture. So say again I'm in R2, There's a vector u and a vector v. I've drawn them so that they have the same initial point. I also have here that in this arrow here, from the same initial point, the projection of vector u onto vector v, which again I went from the end of vector u and drew an orthogonal segment to the line containing vector v, or in this case vector v. And it's dot product, so that is perpendicular when I say orthogonal. Alright, so then this vector is the projection of u onto v. And then if I went from the end of the projection up to the end of u, that vector would just simply be u minus the projection vector, which I've drawn here, going up from the end of the projection to the end of u. Right, so that's the vector u minus the projection of u onto v. Alright, so I've put some notation in here. Here's the theta, right, this angle between vectors u and v. I'll write this off to the side. Theta here represents the angle between u and v. And I should say the non-reflex angle, right? Because I know there's another larger angle, but it's an angle that's less than or equal to 180 degrees, right? Not a reflex angle. Alright, so I say I have this angle theta here between u and v. Now if you look at this picture, I have a little right triangle going on, right? Where the hypotenuse is vector u. So the length of the hypotenuse would be the norm of u, right? This leg is the projection vector, the projection of u onto v. And then this other leg going up in this direction, this other leg is u minus the projection vector, right? U minus the projection of u onto v. Alright, and what you can see from this, right, this right triangle, remember the cosine of an angle in a right triangle. The cosine of and here in my picture, this is definitely an acute angle, is the length of the side adjacent divided by the length of the hypotenuse. So in other words, the length of the side adjacent, right? So here's this angle theta. The side adjacent is the projection vector, right? So the length of this, that would be again the norm. So the norm of the projection vector is equal to the length of the hypotenuse, right? The norm of u, which I got here, multiplied by the cosine of the angle between them, right? The cosine of theta. Right, then I play with this a bit, and if I were to take this norm of u times the cosine of theta and multiply, in the numerator and denominator by the norm of v, the norm of vector v, I'm getting the length of the projection vector is the length of u times the length of v, or the norm of u times the norm of v, times the cosine of the angle between them, divided by the norm of v. And this expression in the numerator, I'm hoping, looks familiar to you. This is hopefully a refresher on dot product. Remember the dot product in Euclidean space. The dot product of two vectors was the length, the norm of one vector times the norm of the other vector times the cosine of the angle between them. So this expression I have in the numerator here is equivalent to just the dot product of vectors u and v. And then we still have the denominator of the norm of v. All right, so the projection, the orthogonal projection of u onto v is a vector, and it's the vector in the span of v. Remember, the span of v is just the line containing v. The projection of u onto v is the vector in the span of v with this norm. Right? as I've shown here, right? The norm of the projection vector is u dot v over the norm of v. So here's a little formula then to give me what is this projection vector? What are the components? How do I find this? So the projection of u onto v is, this is a scalar. This I got this u dot v divided by the norm of v, and I just simply multiply by the the unit vector in the direction of v. Right? If I take vector v here, turn it into a unit vector, right? Normalize it, multiply v by the reciprocal of its norm. This is the unit vector that's in the direction of v. And then I would like to take that, that vector with a norm of 1 and multiply it by a scalar so it has this norm. Right? So I take it's very simple. If I take it, norm of 1, my unit vector, v times the reciprocal of the norm of v, 1 over the norm of v, and multiply it by this scalar, u dot v over the norm of v. There's my projection vector. Okay. So the projection of u onto v, this projection vector, is this scalar. It's u dot v, times 1, so just u dot v divided by the norm of v times the norm of v, so the norm of v squared. So it's this scalar times v. Right, it's because again it's going to be pointing in, it's on the same line as v, so it's just the projection vector is just a scalar multiple of v, and that scalar multiple is one more time u dot v divided by the norm of v squared. And another way to see this, remember the norm of v squared was just v dot v. So another way I could see the projection of u onto v is u dot v divided by v dot v, right, this scalar, times vector v. And I've written this fully on the next page. And we'll go into examples, of course, but just bear with me here for formula development. So in R2, with the inner product being the dot product, the orthogonal projection of a vector u onto a non-zero vector v, because if v were the zero vector, we'd be dividing by 0 in this. Don't want that. So the orthogonal projection of a vector u onto a non-zero vector v is the following, right? So the orthogonal projection of u onto v equals some scalar multiple of v, and that scalar is u dot v divided by v dot v, and then times v, right? Because again the projection vector is on the same line that v is, so it should just be a scalar multiple of v. Now the dot product here was just the inner product, the way the inner product was defined in this case. So this little definition I have here for the orthogonal projection, this little formula, can be generalized to any inner product. So I'm just going to be replacing the dot product with any inner product on some inner product space. All right, so this is generalized to any inner product space in the following way. And I'll show you the very similar. See, the formula is the same. I'm just replacing dot product with inner product, because remember the inner product that's on a space is not always the dot product. Right. So a more general definition of orthogonal projection, and believe me, I will write this formula up for each example we come across in this video. So let u and v be vectors in an inner product space called V, capital V, such that the vector we are projecting onto is not the zero vector, right? Because some problems would happen that we'd be dividing by 0 and stuff, right? It's not good. Then the orthogonal projection of vector u onto vector v is, and again notated the same way, that's PROJ, the projection of U onto V equals, and then again if you're projecting onto V, the result should be a scalar multiple of V. And that scalar is the inner product of U with V in the numerator divided by the inner product of V with itself in the denominator. And then, times vector V. The projection onto V is a scalar multiple of V. Great. Notice how many times V shows up over here, right? The vector you are projecting onto, shows up a bunch. Right? You have it once up here, twice here, and then you're taking the scalar multiple of it. Right? So the vector you're projecting onto is very important. Additionally, the vectors V, the one you're projecting onto, and U minus the projection of U onto V will be orthogonal. And again, this is motivated by my earlier picture in R2. Right, remember this picture here. See, here's vector V, and then this vector I drew going up here was the vector U minus the projection of U onto V. You see how V and U minus the projection of U onto V are orthogonal under the dot product here. They form a 90-degree angle. And that is going to be the case in general. Right, so the vector you're projecting onto and the vector you're projecting minus the projection vector, these two vectors are orthogonal, meaning their inner product will be 0. And I will show you this. We will show you in some examples coming up. Okay. So now for some examples. Now I'm going to start off with, a Euclidean space and the dot product, right, just to kind of ease our way into this. All right, so my first example, and for every example for the rest of the video, I have the following instructions. All right, I'm going to be finding the orthogonal projection of vector U onto vector V in the given inner product space. All right, so in this first example, my inner product space is R2 with the inner product being the dot product, right? So the standard inner product or Euclidean inner product. All right, so my vectors are U is 3, 7, V is -4, -4. Now I'm going to find this projection first without a picture, and then I'll show you a picture. All right, because it is R2, and we should be able to picture things in R2 and R3. Okay, so I'm going to write this formula out again. I'm going to do this for every single one. The projection, right, the orthogonal projection of vector U onto vector V is equal to, again, there's a scale. It's going to be if you're projecting onto vector V, the resulting vector, the projection vector, will be a scalar multiple of V. You'll be on the same line as V, and that scalar is, the numerator is the inner product of U with V divided by, the norm of V squared, the length of the norm of the vector you're projecting onto squared, or the inner product of V with V. All right, that scalar multiple of V. Right. So let's see what we get here. So that's what. Now remember, the inner product is just the dot product. So what's the inner product of U with V? So that's I'll find these separately, actually, off to the side. So what's the inner product of 3, 7 and with -4, 4 there, U with V? And it's just the dot product, so the product of you just take the product of the corresponding components and add them up. So 3 times -4 the product of the first components plus, and then 7 times negative 4, product of the second components, and this is negative 12 plus negative 28. It's negative 40. Negative 40 for the numerator of my scalar. And then what's the inner product of v with itself? So negative 4, 4 with negative, negative 4, 4. So that'd be negative 4 squared plus negative 4 squared. Right? Negative 4 times negative 4 plus negative 4 times negative 4. That's 16 plus 16. That's 32. So the projection of this vector onto this vector, or the line with this vector, the span of this vector, is negative 40 divided by 32. Now, both of these have a common factor of 8. Right, this is negative 8, negative 5 times 8, and this is 4 times 8. All right, so the scalar is negative 5/4 times vector v times negative 4, negative 4. Well, if I multiply v by this scalar, the resulting vector is positive 5, positive 5. So just the vector 5, 5. This vector 5, 5 is the orthogonal projection of u onto v. Now let's see that happen in a picture. All right, let's see this 5, 5 show up in a little drawing. So here I have R2, right? It's the your standard like XY plane. And I have drawn these vectors, right? I've drawn vectors 3, 7 is vector u. Again, so from the I've drawn them both as position vectors starting at the origin. So you see vector u in red is 3 right, 7 up, and every block here, the distance between notches between squares is 1 unit. I'm going to count them as 1 unit. So I've got 3 right, 7 up. Right, so there's vector u. And then vector v I have in blue. It's negative 4, negative 4. So it's from the origin here I'm drawing left 4, down 4. There's vector v. Now the projection of u onto v is, again, I think that should be probably reworded as the projection of u onto the line containing v, or the span of v, right, as I'd mentioned earlier. So let me actually draw that in. Right, what's the span of v look like, or the line containing v? So here's v. I'm just going to draw in here the line containing v. I'll dot it in. Right? Let's make it a dotted line so we know it's not really part of our drawing, but it is, So there's this, I'll say, the span of v being represented. Right, the line containing vector v. And so the projection of u onto v is, remember, I just, to draw that projection in R2 anyway, in R3, I go from the tip of u and I draw an orthogonal segment, so forming a 90-degree angle with the line containing v, or with the span of v. Right. And then this vector is our projection vector. So again, I'm starting from the same point that u and v are, and I'm going to this point at the end of this orthogonal segment. Right? I'm projecting u onto the line with vector v. This vector right here. This is the projection of u onto, again, the line containing v should probably be said more often, but the projection of u onto v. And if you look at this, right, I mean, you look at this vector. I'll turn it this way now, right, back to where count the units. that vector, that projection of u onto v I just drew is, 1, 2, 3, 4, that's 5 to the right, and then 1, 2, 3, 4, 5 up. See that this is the vector 5, 5. Exactly as I said back here when I went through the formulas, right? All right. Now on top of this, all right, on top of this, remember I said the following vectors would be orthogonal. So let me go back here. And on top of this, I remember I did say this statement. Right? We said that. Also, the vector v, the vector you're projecting on, and u minus that projection vector, right? V and u minus the projection of u onto v are going to be orthogonal. All right, let's see if that works. Let's see if that happens here. So v was the vector, negative 4, negative 4. The vector u minus the projection of u onto v, well, that's, u is the vector 3, 7. Minus, and then we saw the projection of u onto v was this 5, 5. So the resulting difference is, the vector 3 minus 5, negative 2, and then 7 minus 5, positive 2. And let's take their inner product. What's the inner product of v with, u minus the projection of u onto v? What's this inner product? Well, that would just be the inner product of negative 4, and negative 2, 2. So that's negative 4 times negative 2. Right, because again, the inner product here is the dot product. Right, just remember to pay attention to how the inner product is defined. I keep saying that, right? Plus, and then negative 4 times positive 2. That's 8 plus negative 8. Hey, look, that's 0. Fantastic, right? That means that these vectors are orthogonal, right, if their inner product is 0. Wonderful. All right, and let me draw that in. All right, let me actually draw the vector negative 2, 2 on the coordinate plane here. Now, if I do that, that would be, now if I could start, remember, vectors can be drawn anywhere. They can start from any point. It's just describing a motion. So negative 2, 2, that's this vector here. Right? There's the vector negative 2, 2, left 2, up 2. Well, you see how this is exactly this vector here that goes from the end of the projection to the end of u. Right? This is the same vector. Right? And do you see how the projection vector, and then this would be u minus the projection. So v and u minus the projection onto v, you can see it right here. They are perpendicular, in this case, because dot product it means orthogonal here. Right? I mean, orthogonal means perpendicular here. Right? So you see how v, and then this is negative 2, 2. This is u minus the projection of u onto v. See how those two vectors are indeed orthogonal. Right? They're forming a 90-degree angle. Wonderful. All right. Okay. So now let's go into an example from R3. Now this one I'm going to pull up a website to draw. My drawings in 3 dimensions aren't the greatest, and in general it's hard to visualize on 2-dimensional sheet 3-dimensional objects, for me anyway. Right. So another example. I'm asked to do the same thing. All right, I'm asked to find the orthogonal projection of u onto v. in this inner product space. So my space this time is R3, right, three-dimensional Euclidean space, with the inner product being the dot product again, right? The dot product is very nice. Just know that because I'm doing my examples with the dot product doesn't mean that the inner product is always the dot product, right? Just be aware of that. Pay attention to how the inner product is defined. All right, so let's look. So I'm going to find what's the now you can do the other way around too. You can project V onto U, but I'm doing U onto V, right? Just make sure you put things in the proper places, right? So what's the projection of vector U onto vector V, or the line containing vector V, right? As you saw in the last example, right? It might not actually go onto V, but onto the line that contains V, or the span of V. All right, well, remember, if we're projecting onto vector V, the resulting vector should be a scalar multiple of V, right? Because you'll be on the line containing V. You'll be in the span of V. So again, this was the inner product of U with V divided by the norm of V squared, or the inner product of V with V. That's the scalar, and then we're on the line that contains V. So this is our result is this scalar multiple of V. All right, so just like the last one, I'll do these inner products off to the side. So what's the numerator of this scalar? The inner product of U with V. Again, this is just the dot product this time. So it'd be 6 times 1 plus 2 times 2 plus 4 times 0. So 6 plus 4 plus 0, 10. And then what's the inner product of V with V? And this is V with itself, the vector you're projecting onto with itself. That's 1 squared plus 2 squared plus 0 squared. So that's 5, right? 1 plus 4 plus 0. So 10 divided by 5, that's 2 times vector V, right? So the projection of U onto V is simply going to be twice vector V, 2 times the vector 1, 2, 0, and therefore that's the vector 2, 4, 0. So this vector here is the projection of vector U onto the line containing vector V, right? Or the projection of U, or the orthogonal projection of U onto V. All right, and one more time with the also, and I'll say this each time too, also vector V, right, the one we projected onto, and the vector U minus the projection vector, right? U minus the projection of U onto V will be orthogonal. So, again, what was V? V is 1, 2, 0. And U minus the projection, right? So let's take U and subtract this pardon me. Take U and subtract the projection vector. So 6 minus 2, 4 for the first component, 2 minus 4, negative 2 for the second component, and then 4 minus 0, 4 for the third component. There's U. And now let's take the inner product of these two vectors and see that it's 0. And can you see that it's 0? Right? You'd have 4 minus 4 plus 0. That's 0. They are indeed orthogonal, and this will always happen with these projections. All right. So the vector you're projecting onto and the vector you projected minus the projection vector, those two vectors will be orthogonal. All right, now let's look at a picture. This time, again, I got a website brought up, the GeoGebra website, the geogebra.org, their 3D calculator here. So here's 624, right? 624 in the red vector there. Here's the vector 1, 2, 0. Now notice that the third component is 0, so it's just on that plane, right? Can you see how it's on that plane with the green and red axes? And you can definitely see that these are not perpendicular already. Just taking a look at these guys here. Okay. So go back to the initial view. And here's the line containing 1, 2, 0. Right, and just drew that line in. Right? The line containing 1, 2, 0, because you see that you're probably going to see that the projection of u onto v is not going to hit v. It's actually going to project onto the line containing v. All right, now I'll bring that line back up when we actually get the projection in. All right, so let me enter. Now our projection was the vector 2, 4, 0. All right, we saw that here. Right, the projection of u onto v was the vector 2, 4, 0. So I'll enter that here. I'll call it vector 3. All right, equals 2, 4, 0. All right, and now you see that's in black. Now look, see how that is? It's just twice vector v. And I don't know, the lining up of the tips doesn't really help. But do you see how that would be if I drew a segment from the end of the red vector straight down to the line, right? The line containing, see that line there, the line containing vector v, the line containing 1, 2, 0. If I drew a segment from the end of the red vector straight down, perpendicular to that line, orthogonal to that line, see how I'd be getting the end of the black vector. All right. Well, maybe that's not as believable, but I don't know. Maybe you can see it in the way I have it set up right there. But let's put in let's put in this vector. All right. Let's put in u minus the projection of u onto v. This 4, negative 2, 4. Let's put in this vector and see if 1, 2, 0 and these look orthogonal, right? And because it's the dot product, we're talking perpendicular. All right, so I'm going to put in another vector, say v4, and equals that, that u minus the projection of u onto v, that 4, negative 2, 4. 4, negative 2, 4. All right, maybe I'll change some colors up. So let's color this one green and this one purple. Why not? All right. All right. So if you look now, see this purple vector. The vector v was the 1, 2, 0. Let me leave that up. I'll leave up the vector 1, 2, 0 and that purple vector. And look at these, right? They definitely form a 90-degree angle. Look at it this way. You can see that the purple vector and the blue vector are forming a 90-degree angle. Right? They are orthogonal. So that projection vector I had up earlier, that 2, 4, 0, was correct. And they're orthogonal as well, right? Because it's just a scalar multiple of v. But maybe you can see it when I do that, right? Definitely a 90-degree angle between the purple and the blue and green there. Okay. But yeah, so projection, hopefully pretty easy to calculate. Again, you just got to pay attention to how the inner product is defined. And one more time here, the vector you project onto, and then the vector you projected minus the projection vector, those two vectors will always be orthogonal. Their inner product should be 0, will be 0. All right. So those last two examples were examples of finding projections of one vector onto another in Euclidean space under the dot product. But there's plenty of other inner product spaces out there, not just Euclidean spaces under the dot product. So that's what my last couple examples are about. Right. So these I can't really picture as well. All right, so this time my inner product space is the set of 2 by 2 matrices, right? R 2 by 2 or M 2 by 2, you might see in some books. The set of 2 by 2 matrices with real entries. With the Frobenius inner product, if you've been watching, hopefully you've seen enough where you've seen the Frobenius inner product. It's like the dot product. the Frobenius inner product of two matrices is just, you just multiply the corresponding entries and then add them up. So you multiply the first row first column entries, the first row second column entries, the second row first column entries, the second row second column entries. You just multiply corresponding entries of the matrices and then take their sum. So it's very similar to the dot product. All right, so here my vectors are matrices, 2 by 2 matrices. Vector u is this matrix with rows 0, 3, 2, 1. And vector v is another 2 by 2 matrix, right, from the same space. Negative 3, 1, 4, 3 are the rows. So what I'm asked to do now is, let's orthogonally project this matrix onto that matrix. Now again, what does that exactly mean? What is, you can't really draw a picture unless you change these things to coordinates relative to the standard basis. Then you'd be basically in R4, but even then you couldn't really picture it very well because R4, four-dimensional space. Can't really picture that very well. But still the same concept holds. I'm going to be projecting one vector onto another. It's just that those vectors are matrices now. But the same rule holds. The orthogonal projection of vector u onto vector v, and again you can switch these if you wish. You could project v onto u if you wanted. All right, just make sure you switch all the letters that I had in previous formulas. If I'm projecting onto v, the result should be a scalar multiple of v, and that scalar is the inner product of u with v in the numerator divided by the inner product of v with v in the denominator, right? And then multiply by v. Right? All right, so what is, again, I'm doing each of these separately. I'll do what's the numerator of this scalar, the inner product of u with v? Again, the Frobenius inner product on a set of matrices is like the dot product, very similar. Multiply corresponding entries of the matrices and then add up their products. So 0 times negative 3, the product of the first row, first column entries, plus, and then 3 times 1, the product of the first row, second column entries, plus, then 2 times 4, the product of the second row, first column entries, and then plus 1 times 3, the product of the second row, second column entries. All right, so we have here 0 plus 3 plus 8 would be 11, plus another 3 would be 14. All right, and then what's the inner product, the denominator of this scalar, the inner product of the vector you're projecting onto with itself, v with v. This is just all these squared added up, right? Negative 3 squared plus 1 squared plus 4 squared plus 3 squared. So that's 9 plus 1, that's 10, plus 16 is 26, plus another 9 is 35. So the projection vector, right, the projection of vector u onto vector v here is 14/35. Now that simplifies, right? This is 2 times 7, this is 5 times 7. So it's just 2/5 times, vector v here is a 2 by 2 matrix, is this negative 3, 1, 4, 3. Or, putting the 2/5 in, just standard scalar multiplication, standard vector addition. Be negative 6/5, 2/5, 8/5, and 6/5. There's the projection vector. Right. The projection of this matrix onto that matrix, in this inner product space. Right. Okay, now let's test it out. Right, if this is true, if this truly is a projection vector, then v and u minus this projection vector should be orthogonal. So again, with every example, I'm writing the same stuff. Right? The vector you project it onto and the vector you projected minus the projection vector are orthogonal. They should be orthogonal. Oops. O-R-T-H. Right. So what was vector v? Well, that's just that matrix, negative 3, 1, 4, 3. And what's this vector here? What's u minus the projection? So it's just, again, standard matrix addition, scalar multiplication here. I didn't redefine those in any way. So I take matrix U, the 2 by 2 minus this matrix. So 0 minus negative 6/5 would be positive 6/5. 3 minus 2/5, that's 15/5. Minus 2/5 would be 13/5. And then 2 minus 8/5, that's 10/5. Minus 8/5 would be 2/5. And then 1 minus 6/5, that's 5/5. Minus 6/5, that's negative 1/5. Right. And let's take the inner product, put wedges around these, and you should get 0. All right, we should get 0. Now, I'm doing this is the Frobenius inner product. So I multiply these first row, first column entries, that'd be, negative 18/5. Negative 3 times 6/5, right? Plus 13/5. 1 times 13/5, right? Plus 8/5, 4 times 2/5. And then minus 3/5. And you see I've got negative 5/5 plus 5/5, that's 0. All right. They are, or these two matrices are orthogonal. These two vectors are orthogonal. Great. So, this is probably the good, the projection vector. I think I did that correctly, and I know I did. All right. So see, it applies to other inner product spaces as well. All right. So I've got just one more example. Because you can do this all day long with any pair of vectors you wish from any inner product space. I just wanted to show a few that weren't, just a couple that weren't Euclidean space here. All right, so this time my inner product space is that C with the closed interval negative 1 to 1. Remember, this is the set of functions that are continuous on the closed interval from negative 1 to 1 on the real number line. With that integral inner product, right, where the inner product of two functions is just the integral from negative 1 to 1 of the product of those functions with respect to x. All right, so my functions here are simple. So vector u, is this function x, f of x equals x. And the vector v is the function I'm calling g of x equals just 1. So x and 1. All right, those are both functions that are continuous on the interval from negative 1 to 1 for sure. So I'm going to project one function onto another, right? Which again sounds weird. Right? How do you picture that? You really don't. Right? It's hard to visualize, but it's still doable. It's still the same procedure, still the same concept. All right, I'm finding the vector on the span of v that would be the closest to vector u. Right? That's what the orthogonal projection of u onto v is. The vector on the span of v in the span that's closest, right, as the shortest distance to u. Okay, so same thing. What's the the orthogonal projection of vector u onto vector v? And again, you can switch these. Just make sure you switch the letters in the formula. Well, if I'm projecting onto this function 1, then my result, the projection, should be a scalar multiple of 1, right? A scalar multiple of v. And that scalar is, the numerator is the inner product of u with v divided by the inner product of v with v multiplied by v. Right? And again, v is just 1. Right? So I'm just going to get a scalar multiple of 1 here. Right, so what are these inner products? Right? What's the inner product of u with v? That would be the integral, right? The way always pay attention to how the inner product is defined. So the integral of from negative 1 to 1 of the product of f and u and v, which are x and 1. So just x times 1. So the integral from negative 1 to 1 of x dx. Right. And this is just 0. So the orthogonal, that means that these vectors 1 and x are already orthogonal. Right. This tells me that x and 1 are orthogonal already. So if we think about this, I mean, I know you can't visualize, c negative 1 to 1, but if we think about it, if you have two vectors that are orthogonal already, so again, say this is u and v here, u going up, v going this way. If they're already orthogonal, and let's say orthogonal means, perpendicular here, the projection of u onto v, remember how I said you can imagine it, go from the tip of u orthogonally to v. Well, you see how that would be just that point there where they meet? Because I'm going straight down. So if u and v are orthogonal already, the projection of u onto v is the 0 vector, right? Just a single point. I'll make that note. And this is the case in any inner product space, not just here. But if if u and v are orthogonal already, then the projection of u onto v is simply the 0 vector, right? Just a single point. And the same would go for the projection of v onto u. If I went from the tip of v orthogonally to u, it'd be just that single point. And the 0 vector does belong to the span of v, right, and the span of u. Right? So this is not wrong if you get the 0 vector. So I'm seeing here that the functions f of x equals 1 and g of x equals x. I'm seeing that those functions are already orthogonal under this inner product. So the projection will be the 0 vector, as we'll see in a second. Right now, let's just finish this off. Take the inner product of v with v. So that's the integral from negative 1 to 1 of v with v is just 1, and that would be 2, right? Antiderivative is x, and then you plug in 1, plug in negative 1, subtract. Right? So my projection vector is 0 divided by 2 times v, 0 times 1, which is just 0, right? Which is the 0 vector in C11, or C from negative 1 to 1. Right. The 0 function would be, that's the 0 vector in that space. So like I said, so this is pretty, this should be happening in any inner product space, what I have down here. Right. If your two vectors are orthogonal, then the projection of one vector onto the other will be just the 0 vector. Okay, as we have seen with this example. So then the statement I made at the end of every example so far would be obvious then. So then v, and remember this, u minus the projection of u onto v are orthogonal. Well, I mean, v is just v, and this time u minus the projection of u minus the projection vector is just u minus 0. This is u. And we've already shown, now remember this little perpendicular symbol means they're orthogonal. We've already shown that they're orthogonal right here. The inner product of u and v is 0. So they are orthogonal v is orthogonal with u is orthogonal with v. Right. But it still holds, right? Everything still holds as it did in the first several examples. You know, the vector you're projecting onto and the vector you're projecting minus the projection vector, these two vectors are always going to be orthogonal. All right, just and it doesn't matter how the inner product is defined. You just have to pay attention, though. Right? You do have to pay attention to how the inner product is calculated. Great. All right, so I think the biggest thing to take away from the video is the statement about just general inner product spaces, which I have right here. Take this away from this video, please. Right. So if u and v are vectors in some inner product space, and the one you're projecting onto is not the zero vector, then the orthogonal projection of u onto v is a scalar multiple of v, and that scalar is the inner product of u with v divided by the inner product of v with v, and then you got, again, times vector v there. And also, this will always happen, the vector v and u minus the projection of u onto v will be orthogonal. Great. All right, so hope this video was informative. Hope the examples made sense and all that. And I hope you enjoyed practicing these. Obviously, you're not going to get better unless you practice. And thank you very much for watching.